Good morning. December 17th, 1903, a cold, windy day at Kill Devil Hill, North Carolina. Two brothers, bicycle mechanics from Ohio, achieved the impossible for 12 seconds. Their heavier-than-air machine, the Wright Flyer, sustains controlled, powered flight, covering just 120 feet. In that moment, Orville and Wilbur Wright didn't just fly. They rewrote the future and etched their names into history forever. Just over 2 decades later, a young airmail pilot named Charles Lindbergh strapped himself into a single-engine monoplane, the Spirit of St. Louis. We remember the triumph, but we also often forget the sheer audacity of the aircraft's design. It was a radical, unconventional machine, purpose-built to do one thing at the expense of all else. To achieve the necessary range, the plane was essentially a flying fuel tank with a cockpit tacked on as an afterthought. Lindbergh famously had no forward-facing window. The main fuel tank was placed directly in front of him for center of gravity and safety reasons, completely blocking his view. To see forward, he had to use a small slide-out periscope. He bet everything on a single engine when everyone said multiple engines were necessary for safety. He was ruthless in his pursuit of efficiency, stripping out every non-essential component. The radio, a parachute, even the standard seat was replaced with a lightweight wicker chair. It was a design exercise in obsessive weight saving, and it was that radical engineering that made the impossible flight a reality. And then there was Igor Sikorsky, a visionary who dreamed of vertical flight. In 1939, he lifted off in his VS-300, a strange and wonderful contraption of tubes and rotors. It was tethered, and the flight was short, but it was the dawn of a new era. Sikorsky had built the world's first practical helicopter, a machine that would go on to save countless lives and redefine mobility. The Wrights, Lindbergh, Sikorsky, these aren't just names in a history book. They're reminders, they are proof that a bold idea, whether from a person or a team, can defy convention and change the world. They faced the monumental challenges of their day, control, endurance, and vertical lift, and they conquered them. I'm Phillip Smith, the program manager for the DARPA Lift Challenge. It's an honor to be here at the Vertical Flight Society because I believe that we are at another one of those historical inflection points. We stand before a new fundamental challenge, and just like our predecessors, we have the opportunity to conquer it and be written into the history books. Today, I want to talk about how we can shatter the modern heavy lift bottleneck, the payload to weight ratio, and together unlock the next revolution in vertical flight. The Wrights, Lindbergh, Sikorsky, these pioneers answered an innate human challenge, but what if we could formalize that spirit of competition to accelerate innovation? History shows that well-crafted challenges are one of the most powerful tools for sparking a revolution. In fact, the very flight I mentioned, the Lindbergh's transatlantic crossing, was directly spurred by a challenge, the Ortigue Prize. In 1919, a New York hotelier named Raymond Ortigue offered $25,000 to the first aviator to fly nonstop from New York to Paris. For years, the prize lay unclaimed. Established, well-funded teams failed. Then a small, relatively unknown team from San Diego backed a determined airmail pilot. Lindbergh's victory wasn't just a personal triumph. It was a global event that electrified the public and supercharged the aviation industry. This model, posing a grand challenge and incentivizing a diverse community of thinkers to solve it, is deeply embedded in DARPA's DNA. Many of you will remember the DARPA Grand Challenges of the early 2000s. In our first one, we posed a seemingly impossible task: build a vehicle that could drive itself completely autonomously across the Mojave Desert. At that 2004 event, the scene was chaos. The best team from Carnegie Mellon made it only 7.3 miles before their vehicle got stuck and its tires caught on fire. Not a single vehicle finished. Critics said it was a foolish waste of time, but they persisted. They held the challenge again just 1 year later. This time, 5 vehicles successfully completed the entire course. The alumni of those DARPA challenges are now the leaders of the autonomous vehicle companies that are poised to change transportation forever. The Grand Challenge took a niche academic pursuit and turned it into a multi-billion-dollar technological revolution. Time and time again, we have learned that when the goal is not just incremental improvement, but a fundamental leap forward, a challenge is a highly effective tool. It attracts visionaries from every corner, from established labs to the quintessential American garage. It rewards daring and unconventional ideas. That is why we chose this format for the lift problem. We're not looking for a slightly better rotor blade or a marginally more efficient engine. We're looking for a paradigm shift. So what is the specific stagnation that we aim to break? The truth is, the world of vertical lift is currently constrained by the conventional application of its core designs. First, let's consider the classic helicopter. Sikorsky design was a masterstroke, but we must recognize that its architecture was engineered around the capabilities and, more importantly, the limitations of a human pilot. The entire system is built for a human to control it and survive while flying. For over 80 years, we have brilliantly iterated on this human-centric model, but we have yet to truly break free and fundamentally rethink vertical flight for a mission where there is no pilot to protect and no human biology to consider. Then we have the quadcopter. This architecture has been revolutionary, putting flight into the hands of millions, but its common implementation has a limitation. It achieves lift primarily through brute force, by simply pushing air down. This reliance on pure thrust has to date proven difficult to scale efficiently to heavier weights. When you attempt to lift heavy loads, the power requirements, acoustic signatures, and economic costs grow exponentially. But this does not mean the quadcopter is a dead end. It means we must challenge its current implementation. What if a multi-rotor platform wasn't just about brute force? What if it was fused with revolutionary aerodynamic innovation that shared the lift burden? What if a breakthrough in its powertrain could fundamentally alter the efficiency curves? The architecture isn't the problem. The reliance on a single inefficient method is. This brings us to one of the most discussed barriers to heavy lift, battery power. The eVTOL world is filled with brilliant engineering, as we can see here today, but we've seen a hyper-fixation on pairing batteries with designs that are incredibly power hungry. The challenge arises when the demanding physics of vertical flight are met with the current energy density of batteries. This combination has so far limited the practical adoption of these systems for meaningful work. But this is not an argument against batteries. It's an argument against inefficient systems. A breakthrough aerodynamic design that requires a fraction of the power to hover could suddenly make batteries a viable, even ideal solution for heavy lift. The problem isn't the battery itself. It's the massive load we are asking to carry in an inefficient concept. So this is the landscape. We're not stuck with dead-end technologies. We're stuck in patterns of thinking that keep them in separate, inefficient silos. The DARPA Lift Challenge is designed to break these patterns. We're asking you, can you combine these ideas in new ways? Can you invent a new powertrain that makes a quadcopter scalable? Can you design an airframe so efficient it unlocks the potential of batteries? The goal is not to discard these conventional ideas, but to be the one who finally breaks the rules. So before we dive into the details of the challenge, let's pause and ask, what does success actually look like? What world does a 4-to-1 payload to weight ratio create? And why is this so important? So you can see here, picture a landslide in a remote mountainous region. The roads are gone. A small disaster relief team arrives in a single Jeep. They unbox a 50-pound drone. They attach a 200-pound payload of emergency shelters, water, purifiers, satellite phones. Within minutes, that crucial aid is airborne, flying over the impassable terrain and landing in the isolated village, all without a runway, a multi-million-dollar helicopter, or risking a flight crew. That is humanitarian aid at the speed of need. Now picture a small infantry squad on a contested battlefield. They're running low on ammunition, and their radio batteries are dying. A vulnerable ground convoy is miles away and would draw fire. Instead, an autonomous 50-pound drone is launched from a base 20 miles away. Flying low and quiet, it evades detection, arrives at the squad's position, delivers 200 pounds as a resupply, and returns automatically. It's logistics at the speed of relevance. Taking trucks off the roads and helicopters out of the sky. Think about our own cities. A construction crew building a skyscraper needs to get a heavy tool from the ground to the 40th floor. Instead of a complex and time-consuming crane operation, a small drone picks it up and delivers it in minutes. Now, of course, these are all examples of what small drones could do with that kind of a payload-to-weight ratio. When we think bigger, we can see an even more dramatic future. A Black Hawk-sized aircraft could lift what a CH-53K can lift today. Imagine the capabilities that this would open up when the production and operations of heavy lift is reduced so dramatically. This is the future we are trying to build, a future where heavy lift is decentralized, affordable, and accessible to more than just the largest organizations. So you might be asking, why now? If this problem is so fundamental, why does DARPA believe a breakthrough is possible now? The answer is that we are living in an unprecedented era of technological convergence. For the first time, several distinct revolutions are maturing simultaneously, and their tools are accessible to everyone. First, materials and manufacturing. A decade ago, creating an airframe with a world-class strength-to-weight ratio required an industrial-scale composites lab. Today, advanced carbon fiber, Kevlar, and other composites are widely available. More importantly, the explosion in additive manufacturing, 3D printing, allows teams to design and create complex, lightweight structures with internal trusses and optimized geometry that were literally impossible to fabricate before. A small team can now print parts that were once the exclusive domain of major corporations. Second, the power revolution. We've all seen incredible progress in electric motors, driven by the EV and drone markets, leading to astonishing power density. But happening in parallel is a quiet resurgence in ultra-lightweight, power-dense internal combustion engines from the high-performance UAV and hobbyist worlds. This isn't an either-or choice. For the first time, a designer has a rich menu of options: pure electric, advanced combustion, or hybridization, combining the best of both worlds. Third, the aerodynamics revolution. Not long ago, testing a radical new wing design required millions of dollars in a wind tunnel. Today, the democratization of CFD, computational fluid dynamics, means a team with a powerful laptop can simulate, test, and iterate on dozens of designs. This opens the door to exploring concepts beyond simple rotors, ideas like circulation control, co-flow jets, or distributed propulsion at a speed and cost that were previously unimaginable. Your ability to innovate is no longer limited by your access. Finally, the control revolution. The rise of powerful open source flight controllers has been the silent backbone of the drone boom. These sophisticated brains can be adapted to stabilize almost any aircraft configuration, no matter how inherently unstable. This is a profound shift. It frees designers from the old constraints of having to build a stable airplane. You can now design a vehicle that is optimized for pure aerodynamic and powertrain performance, and trust that the software can handle the challenge of keeping it in the air. For the first time in history, all these tools are on the table. The materials, the power systems, the simulation tools, and the control software are mature and accessible by the general population. The ingredients are here. The question is, who will be the first to combine them in the right way? Okay, so how did we get to DLC? The path to the DARPA Lift Challenge, DLC, was a personal journey for me. I came to DARPA with a passion for heavy lift and logistics. After taking on a couple of drone programs, I organically just became known as the drone guy in the agency. And this role gave me a really unique privilege. The opportunity to speak with innovators all across the country. I talked to people in established companies, university labs, and garages, and I saw a reoccurring theme. They were brimming with ideas that went far beyond the conventional. They were sketching designs that challenged the very foundations of vertical lift. To formalize this, we put out a request for information, or RFI. It was called Cost-Efficient Cargo. The response was phenomenal. It confirmed that an incredible number of organizations had already been thinking outside the box, completely independent of us. But an RFI on a government website like sam.gov only reaches so far. We knew that for every brilliant idea we saw, there were likely 10 more we were missing. To truly capture the full spectrum of American ingenuity, we had to go bigger. We had to go more public. Right as we were grappling with this, the timing became perfect. The administration issued a new executive order with a clear mandate for ensuring American dominance in drone technology. Suddenly, our pursuit of radical innovation was perfectly paired with a national strategic imperative. But even with a great idea and top-level support, there was a major bureaucratic hurdle that could stop the best ideas. FAA's Part 107 weight limit. We all know the rule, right? Under 55 pounds, anything bigger and you might as well be working with a Boeing 777. How can you demonstrate heavy lift if the rules keep you grounded? So this is where I'm really particularly proud of the groundwork our team has done. We didn't just announce a challenge and leave the regulatory navigation for teams to figure out on their own. We went to the FAA as a partner. Through an amazing period of coordination, we have forged a clear pathway for challenge participants to safely and legally fly systems that exceed the standard weight limit, while not being burdened by the administrative process of heavier aircraft. We've cleared the bureaucratic runway. In fact, I just posted a video yesterday with the Director of Rulemaking from the FAA explaining this entire process. So with an obvious need, a confirmed groundswell of hidden innovation, a national mandate, and a cleared regulatory pathway, all the pieces were in place. So the DARPA Lift Challenge was born. Okay, so what does this challenge actually look like? We designed it to be simple in its rules, but radical in its ambition, focusing on one key metric, payload to weight ratio. Here's the core mission: design and fly a system where the aircraft, including its power source, weighs no more than 55 pounds. That system must then take off vertically, lift a payload of at least 110 pounds, and complete the competition course. The winners will be the ones who complete the course with the highest payload to weight ratio. Now let's talk about the why behind this structure. Innovation and rules often feel like polar opposites. But for the challenge to be fair, we must establish a level playing field to compare vastly different designs. We've worked hard to make these rules as unconstraining as possible, focusing only on what is absolutely necessary for safety, fairness, and the practicalities of operating a live event. The course itself is a straightforward 5 nautical mile circuit, but its design is anything but arbitrary. We look at this course kind of like the 800-meter race in track and field. It's agonizing distance for a pure sprinter, and it's an all-out sprint for a marathon runner. It's intentionally hard because DARPA is supposed to do hard things. This distance demands a unique blend of raw power and sustained efficiency, and it will reward the most well-rounded and robust systems. Critically, the course profile is something your teams can practice from home, staying within standard Part 107 rules during your development, and then under the exemption that we're going to do with the FAA to go above that 55 pounds. So this was a deliberate choice. We want teams to spend their time and money on design and testing, not on extended travel and time at the challenge site. Most importantly, this structure gets to the heart of our goal. Previous drone competitions have bundled flight performance with tasks involving autonomy, sensors, and complex mission software. We're unshackling competitors from that. This is a challenge of pure aviation innovation. By focusing on a simple metric, how much can you lift relative to your weight? We are steering the competition away from who has the best sensor suite or the most complex algorithm. This also dramatically lowers the barriers to entry. You don't need to procure or develop expensive sensor packages or autonomy stacks. We want every dollar of a team's resources and every ounce of their brainpower focused on a single goal: rethinking what is possible in aerodynamic and powertrain design. This principle is embodied by the payload itself: cast iron Olympic barbell plates. Simple, dense, and undeniable. There's no room for misinterpretation. It's a pure test of lift. And for the first time, actually, oh, there's my video. Yep, pretty proud of that. Made that in PowerPoint. And that's the course. All right, so for the first time, we're actually announcing here at VFS the location and the date of the competition. So we're looking to hold it at the National Museum of Air Force, Air and Space Museum at Dayton, Ohio, with the 88th Air Wing there, August 2nd through 9th. And this is a layout of our proposed. It's not finalized. But we're excited that Flight Fest from the great organization Flight Test, if you guys haven't seen their YouTube videos, you're missing out. They're actually going to be joining us. So they're over there on the left side in the black. They have their camping sites, all of their STEM courses for kids, and then their flight area at the bottom. And on the right is all of our lanes that are set up. So whether we go north, south, east, west, doesn't really matter. That's about what it's going to look like. So we believe that this is not only going to be an amazing innovation event, but it's also going to be really fun for both the teams and the general public to come and experience what the joy of aviation is all about. So I want to leave you with this. The Wrights, Lindbergh, Sikorsky, they weren't just engineers. They were visionaries who refused to accept the limitations of their time. They now stand as giants in the story of human achievement. We now stand at an inflection point facing our own set of limitations. The DARPA Lift Challenge is more than a competition, it's an invitation. An invitation to everyone in this room and in garages and labs across the country to join that legacy. This is your chance to solve a fundamental problem in aviation. This is your chance to build the future of vertical flight. This is your chance to be written into the history books. Thank you. And I guess we have 5 minutes and 54 seconds for questions.
Yeah, we'll take a few questions and then we'll feed you guys, I promise. So if there's any questions for Donna.
One question here.
Man,
so,
these lights are no.
Yeah, they are pretty bad, aren't
They're
they?
ridiculous.
With regards to the 44807 that you alluded to, I'm sorry I haven't seen the video from yesterday. It's so late breaking.
It happened.
But for those that are interested in this, will they have access to get above the 55-pound limit with the 44807 before the August 2nd date at their location? Or will they have to separately approach the FAA and go through that process?
Nope. So the way we purposely designed it is that you can build your aircraft under 55 pounds, start test flying, right? I'll be submitting the 44807 exemption here in another week or two, and then it takes them 120 days But we've done a ton of pre-coordination, so that actually should be shorter. So around the May timeframe, May-June timeframe, it's FAA, right? It's out of my hands. But around the May-June timeframe is when people will start to fly at home in their own, approved airspace for Part 107 operations.
So there'll be some addendum process that individual challenge teams will have to apply to then get on that with you?
Correct. So you would just apply to us on our website here, the DARPA Lift Challenge website. You can also go to the DARPA homepage and find the challenge details there. When you are a registered person with the DARPA Lift Challenge, you'll go into the appendix of the 44807. We'll email that to you, and you'll print it out, and you'll be legal to fly.
Okay, great. Thank you.
Here.
Okay.
Yeah, so on the mission, right in the end, you have that 1 nautical mile unloaded. And even though I have my own opinions on that, I've heard some comments, I wanted to know what DARPA is thinking or expecting from this. Is that related to controllability or something?
So that was exactly it. We knew that when you're getting up to that 4-to-1 payload to weight ratio, an aircraft is going to handle drastically different with weight and without weight. And obviously, because this is a logistics or a Amazon delivery kind of concept here, you have to fly home unloaded. So if you built a design that could only fly at full weight but couldn't fly unloaded, it's kind of useless for any sort of application.
Hello.
Hi.
So you mentioned in your earlier slides that you listed a lot of earlier challenges that DARPA did, and you also, for this position, you list mostly your requirements and what you want from the challengers, right? But I know that most of the challenges you listed on the DARPA page, most of them did not result in anything that was successfully fielded. So how do you ensure that this challenge in particular will result in a successful contender?
That's a great question. You don't. That is the risk that we all have to take on every one of our papers that we write or the things that we do in our labs is you don't know, but you still do it anyway. Because maybe in 5, 10 years or 75 years for the Army, they'll get a tilt rotor. Sorry, I'm a Marine, so we got to tilt rotor first. So you never know, but you still pursue it. And you still go after it, right? And that's what we do. That's what DARPA does. That's what you guys do as academics and vertical flight societies. You dream of the future and you start going in that direction.
Yeah, can I ask you a question about the course that you have from the last slide?
Yeah.
So I'm represent one of the teams, and I would love to request if you could just move those courses down so that the takeoff was from the runway.
Yeah, so
grass is really hard to land and take off.
It is. So we're going to have actually someone suggested these little stages is what we're going to rent and we're going to put down. So you'll actually be taking off from a stage, not on the grass.
Not runway?
Not the runway. It goes into a lot. Believe me, we have looked at like 1,000 iterations of things. That runway is like pitted and old. So you really don't want to be landing on that either.
Okay.
But yeah, we're going to have a nice raised stanchion or stage.
Okay,
piece.
and the second question kind of follows on with that. In your diagrams, you have the starting and landing area somewhat inside of the alleys.
The geofence, yep.
The geofence. How far inside are you planning on having those? In other words, so the course is a quarter mile. Is it a quarter mile plus 100 feet?
No, so
or do we have to do one extra turn?
Yeah, we haven't laid it down because actually we're still talking with the FAA on safe separation between buildings and people. So we're making those rules up. We're actually doing exemptions. So we have to get into the math of blade sling and all that sort of stuff, right?
Yeah, you go.
So right now we're at 100 foot by just over 1,000 feet is that course that you see there. If we have to go to 500 foot separation, we're going to have some problems. If we can keep it at like 200, 250, that's one of the reasons we reduce the altitude.
So the quarter mile is not hard. The quarter mile distance, it could
I know
be
everybody's
less.
asking, and we're trying to get the dimensions out, but there are so many factors that go into how this course is laid out, and
Because those, as I got to say, as a designer, those hover turns are absolutely critical. If we have 16, it's a vastly different number than if we have 20.
Agreed.
Okay.
It's hard, isn't it?
Well, it just, you can't design for it until you know.
Believe me, the emails I get from people about this is just hard. Yes, it is supposed to be hard. Sorry, I'm not saying that.
I like
to you,
hard. I just want to know what it's going to be.
I know.
Because I
I know.
can't.
And I would too as a performer, so or as a competitor. But we're trying.
Okay.
We'll get it to you as soon as we can.
Great. Thanks.
Yeah.
What's the prize?
Oh yeah. Glory. Yeah, so this is a funny story. I started out with, it's $6.5 million of total prize pot. The way that's broken down is first, second, and third get some. If you don't get over the, so it's like $2.5 million. Sorry, numbers off the top of my head, $1 million and like something like that. If you don't get over the 4-to-1, you only get 50% of that prize pot. If you get over the 4-to-1, you get that whole prize pot. And then there's 3 subjective categories. So I'm going to have a panel of DARPA PMs who work all in aviation projects. And so there's a most revolutionary aerodynamic, most revolutionary powertrain, and then most promising. And the reason for that is for everybody who's worked in aviation, which is this entire room, you know that we crash a lot. That doesn't mean it's a bad idea, right? So if I only went with the safest options and those got first, second, and third and got national recognition, we'd be losing the innovation of the people who really tried to push the boundaries. So we're saving those subjective categories. And those are all $500K each.
Thank you.
Okay. It is lunchtime.